Lesson today is a learning target 3.8 that you can explain the relationship between the mass spectrum. So that's something that you'll learn what that is today of an element and the mass of the element's isotope, something that we talked about in the previous lesson. So let's get started. So the technique we use to do this, and we actually don't have the capabilities at our high school to do this, but any college laboratory, professional laboratories has what's called a mass spectrometer. Mass spectrometry is the ability to separate these things. So let's go back to Dalton's atomic model. So one of the things that he said was that all atoms of the same element are the same, but atoms of different elements are different. So this part, all atoms of the same element are the same, is not true. We saw that in the last unit or the last learning target. Isotopes exist. Isotopes are atoms that have the same number of protons, but they have a different number of neutrons, which makes the masses different. For example, the natural isotopes of oxygen are oxygen 16, oxygen 17, and oxygen 18. They all have 8 protons, but this one has 8 neutrons, this one has 9, and this one has 10, which actually makes them different from each other. So what we're able to do using a certain instrument that I'll describe next, we're able to separate these from each other and figure out how many we have of each in a sample of oxygen. So here is what the instrument looks like. So it's a technique that allows us to experimentally determine the relative averages. So overall, what we do is we start, let's go back there. I'm looking for the pointer. There we go. The sample enters here and then vaporize the sample and speed it up a lot and then send it through a corner. And that corner has a magnet on either side. And that is what is going to allow us to separate the isotopes based on their sizes. This can also be used for different atoms as well, but we're going to focus on the isotopes for it. So let me get a little bit more into what's going on in this area. So here we go. So one of the things I noticed that a handful of Greendale seniors has are mopeds. Other students arrive on buses. So I want you to think about these two things. And as these two things, if you're riding in a bus, driving a moped, and you need to make a corner, I want you to think about how easy it is to make a sharp corner. And most likely you're thinking, oh, well, the moped can make a really sharp corner, and that's right. So if we start out these two things, the bus has a lot of mass, the moped does not have a lot of mass, and we send them through the mass spec, what starts to happen is as they turn that corner, the moped has a lot easier time turning the corner than the bus does, and so they're able to separate from each other. Same idea with isotopes. We are able to send isotopes through, and we get lighter isotopes registering on one part of what we call a detector, and heavier isotopes measuring somewhere else. So we don't obviously run buses and mopeds through this, but we do run samples through it. So if we took a sample of ZR, which is zirconium, zirconium actually has 5 different natural isotopes. So if we were to send that sample through and read what we get something that looks like this. All right, so I'm going to walk you through this graph a little bit. So on the bottom, we have the atomic masses. So this is just going to be, notice we've got the same numbers as we do here, those atomic masses. Then we also have relative abundance. So when we have these isotopes, as we saw in that last lesson, we don't have the same amount of each one. There tends to be one that dominates and then smaller percentages of other ones. So as you run the sample through, this ZR90, there was a lot of these isotopes that were in the sample, and so we say it has a high relative abundance. So you can imagine if we had this detector that the 90s just kept hitting it, 90, 90, 90, 90, 90, with so many of them, and just like a couple 96s, maybe one 96, I'm going to give a whole bunch more 90s. So they all hit here, and then a couple 91s, and then there were some 92s and 94s. All right, so we're able to take how many times it hits that detector and turn it into a graph. So if we look at this, let's kind of break down these numbers. What we're looking at is a ZR90 from reading this, I'd say that's about 51. And this is one of the things we're going to want you to do. We want you to take these mass spec images and figure out the percentage of each one. So I got 51 in the first one. I'll let you kind of look ahead on the other ones and jot the numbers down. So we've got 11 on this one, probably about 18 here, about 18 here, and about 2. And they should add up to about 100. If you're really off, look at it. If you're off by a little bit, hey, that's okay. All right, so now that we can read these, what are we going to do with it? I bet you're all wondering that. So what we want you to be able to do is turn this data into the average atomic mass. So with all of these percents, I am able to read them from the graph. So our first step is going to be reading the information from the graph. So I look at each one. I'm just going to put a little line there. And I'm going to do my best to estimate what that value is. For this 24, it looks like it's pretty much right on or a little bit below this 80 line. So I'm going to call this one 79. For the 25, it looks, so I've got the 25 and 26 that are super close to each other. I'm going to say this one's about 10 and this one's about 11. Again, I'm kind of looking at these numbers. They add up to be 100. So now I need to do my second step. I need to use this to calculate the average atomic mass. Well, this is very similar to what you were doing on Monday, where you take each of these percentages. So I've got 79%, which I turn into a decimal, so it's 0.79, and then I multiply that by its mass, times 24. And then I do the second one. So I've got 0.10 times 25, and then 0.11 times 26. All right, so go ahead and put this in your calculator and calculate what it is. When I calculate those and I left them as each of the separate things, each of the separate multiplications, I add them together, I get 24.32. And then looking at the periodic table, it looks like this element is magnesium, which is what it is. So that's one of the things we want you to be able to do. If we give you a graph that looks like this, we want you to be able to figure out what the average atomic mass is. And again, these are using weighted averages. Same thing we talked about earlier. Also, same thing as we calculate your grades. Your grades are 70% tests, 30% labs. So we average those scores together and weight them, and then we get the final grade. All right, let's go to the next one. All right, another thing that we want you to be able to do is do the reverse, where we give you the isotope and the percent abundance, and we want you to be able to put it on the graph. So go ahead and start working on this, but if you're not sure how to do this, you can stay with the video. So what I have is, I can see the first one, 204, which I see right down here, and that is about 1.4%. I need to check my y-axis, so this is every 10. So this one's gonna be really, really short, but I just need to get it on there. And then the next one is 206, and I need 24.1. So 206 is here, 24.1 is gonna be just right about there. And so I have a line there. Then 207 is going to be 22.1. So that's going to be just under this. So let's try about there. And then 208, 52.4, which is the mainly net occurring isotope of this one. So maybe somewhere in there. There you go. So those are the two skills that you need to be able to do for this learning target. And then there is a worksheet that goes along with this that you can start working on. And again, let your teachers know if you have any questions on it.